Morning. I am Rufyid-U, second year PhD candidate from Indian Institute of Technology, Bombay. It's really hard to follow two fabulous talks, but yeah. So during a PhD, I'll be working on design and development of physiotherapy assisting products. And right now I'm leveraging inertial sensors for it. So here I'm presenting the work Embedded Machine Learning on Accelerometer data for exercise classification. I'll walk you through the motivation behind doing this work. The developed device, the methodology of embedded machine learning, the results, and the conclusion of the work done. So the traditional physical therapy system, it involves continuous visits to the clinic, or the patient needs to be in the hospital or the clinic till the rehabilitation is complete. This turns out to be very expensive and inconvenient for the patient. Remote rehabilitation will enable early discharge of the patient from the hospital, and the therapist can monitor and assess the patient while the patient can perform the exercise in home environment. This will also increase the adherence to exercise, as the therapist can monitor the patient at a regular pace. To promote remote rehabilitation, we require physiotherapy assisting products, which can be also cost effective and help the therapist monitor the motion. So we have available camera-based sensors which need to be installed in a restricted environment. The camera sensors capture the human motion, and the data collected from the camera sensors is continuously being uploaded on the cloud, which runs high computational algorithms and neural networks to understand the motion done by the patient, classify the exercise done by the patient, and then the therapist, the information goes to the therapist. We can use low-cost motion sensors such as accelerometer sensors, and to ease the patient recovery. And here we can use embedded machine learning to leverage on the device. In embedded machine learning, the sensing, processing, and the classification can be done on our device, on our microcontroller, in contrast to the cloud-based sensor, in which the continuous data needs to be uploaded to some place. This using camera sensors also raises the concerns of privacy, which is not a concern in case of using motion sensors. So this work is done with the concept of having a patient-friendly device, a wearable device, and also which does not have the concerns of privacy. So in this work, we have used a single wearable unit, which can be worn on our lower limb, and the patient can perform the exercise. Here we have used accelerometer sensors. Microelectromechanical systems have miniaturized the inertial sensors, miniaturized accelerometers, such that they have very small size and weight and can be easily integrated into a wearable band. Also, they come in a very low cost. In here, embedded machine learning is leveraged on the raw accelerometer data to understand the 3 exercises which are recommended by the therapist for the lower limb rehabilitation. So the embedded ML is a 2-stage process, training and inference. In this project, I have used open source platforms, Edge Impulse and Arduino, for completing this device. So Edge Impulse is for the training purpose, and the inference is on our device, which is Nano 33 BLE Sense. The process of embedded ML is collecting the data from our device, training our model, which should be really optimized because it has to be run on our resource constrained device, which is here Nano 33 BLE Sense. Then the same model is deployed back on the same device from which it was trained. So the methodology for training is as such. First, we need to do the data collection. The data collection is done from our 3-axis MEMS accelerometer, which is present on board Nano 33 BLE Sense. And the 3 exercises are done, and the data is collected and uploaded for training on our platform Edge Impulse. So after the data has been collected, we have split the data so that we have some data for the validation and the test. The training set data, which is 60% of the data collected, is then used for creating the machine learning pipeline. So for the embedded machine learning, we don't just feed the raw data directly into our black box neural network. We first do some feature extraction, and then the features extracted from our raw data is given as an input to the neural network. The created pipeline is tested and evaluated using the standard evaluation tools of our machine learning. After that, the model has been created, the library is created from our model and then uploaded on our device, which is a Nano 33 BLE Sense. So signal processing is the key of embedded machine learning, because uploading the raw data, it is not possible to be run on our resource-constrained device. So when I sample with 100 Hertz and inference I'm doing with 2 seconds, and here I have 3-axis MEMS accelerometer. So for 2 seconds, I have 600 raw samples. But when I do the feature extraction, I am reducing it to 11 features generated per axis. 3-axis MEMS accelerometer I'm used. Therefore, I have 33 features as an input to our neural network. And thus, signal processing drastically reduces my neural network architecture. So then the model has been deployed on our board, and the inference is the procedure of seeing whether the model works on our live, unseen data. The exercises are done, and the probability of which exercise is done by the patient is seen here. So the created model is evaluated using the standard tools, that is our confusion matrix, which truly shows that it can classify the exercises properly. The F1 score is around 0.99. The inference performance matrix tells us in how much time does it take to do the inference on our device, which is around 8 milliseconds for 3 exercises, which I have used right now. And the machine learning pipeline uses only 7 KB of RAM of the available 256 KB RAM on our board. So after the model has been deployed on our Nano 33 BLE Sense, I have powered it using the LiPo battery, and the components have been fitted into a customized 3D printed box, which can be worn anywhere on our lower limb and is fitted on the limb using the Velcro strap. A web app has been created, and it collects, it just detects the inferred exercise from our device. The raw data processing, everything is done on our device, just the inferred exercise needs to be communicated. So right now, the data set is from a healthy patient, collecting data from the patients which actually require rehabilitation will be better. And right now, the device can be worn anywhere on a lower limb, but it has been trained to be worn on a lateral side, facing outwards, because it's an accelerometer and it senses the directions. If it's worn in any other orientation, it will not give proper results. Also, in the future work, I'll include the incomplete exercises. For this, we need to measure the range of motion, which can also be done by leveraging just the accelerometer sensor. and it will tell us the incomplete exercises done by the patient. So yeah, embedded machine learning helped us optimizing the machine learning pipeline and can classify the exercises. The model created is run on our ARM Cortex M4 processor, which is present on the board. It overcomes the restrictions of the camera-based sensors, as the patient can do it in any environment without the restrictions of a room where the camera needs to be in a particular orientation. Also, all the processing and the inference is done on our device, so there's no need for even cloud computation or even high powerful computers. Yeah, thank you. I would like to have your feedback.